Everyone. Hope you're having a nice asynchronous Wednesday. I'm going to walk you through in your lesson today the background lecture for activity 29. Since I'm going to lecture to you in this asynchronous day, I'm not going to short you your pun as well. So we'll start with that. Here's sort of a visual pun here. We've been studying charged objects. We've got a joke here involving the cow. One of the things we're going to start to learn as we get a little less abstract with charges, we start to look at electrical devices. We're going to see what's called schematic symbols, diagram symbols for drawing things in circuits. This symbol right here, the three lines, and this is like a wire, and the three lines are for electrical ground. Ground is when you take a charged object and you touch it to something that's big, like the Earth. The Earth is a big reservoir that can take or give electrons without changing its charge. So if you attached a cow to the Earth, then the cow is in a sense grounded, and any charge that's on the cow can get off and neutralize the cow. So this, my friends, you're looking at ground beef. Optical illusion, you see them everywhere. You could even be an optical illusion. This guy thought he would get a tattoo. Kind of looks like an MC Escher drawing. I don't know. We'll see what Mrs. Philman thinks. I'm thinking about getting one of these. It's a good conversation piece. Our objectives for today, we'll do the background lecture for activity 29. I'm going to move a little quickly through it. I won't be actually writing all of the notes out, but more talking through the notes that I've provided for you already in Canvas for activity 29. And as you guys have questions, you have kind of two recourses if something's not making sense. You could jump into the Google Classroom, send me an email, jump into to our meeting, not Google Classroom, Google Meet this afternoon, and I'd be glad to meet with you and answer questions, or we'll have work time to finish up activity 29 tomorrow, and you could ask questions then if you prefer. You do have activity 28 due today, so the same thing holds for that. If you want to meet with me this afternoon and you have questions or need help with activity 28, more than glad to do that. Just send me an email. The only assignment that you have to work on for next class is the donor video on resistance. So it's not a reading assignment from your textbook, rather a video I'd like you to watch. You'll find that under reading assignments in Canvas. So that's the plan for today. I'm going to go ahead and get started since there aren't any questions. I don't have you guys here with me live to tell me I'm not switching my screens correctly, so hopefully I do it right this time. All by myself without any help. Okay, so what do we got? We're looking at the background lecture for activity 29. And we have the topic today is current and resistance. Current and resistance. So like I mentioned before, all this abstract stuff with fields and potentials and force fields in space, charges coming from infinity and coming in, that's very abstract. We're going to get much more concrete, practical, building the foundation for understanding electrical devices and electronics in everyday life. So let's start off with this image right here. And kind of explain what it is that we're looking at here in this graphic. So in this picture, I have a section of a cylinder. Maybe this is a piece of wire, a conductor through which we're going to run electric charge. So rather than just having charge sit still, we want to have it flow from one place to the next. So one way that we could do that is by having a potential difference, a place of high voltage and a place of low voltage. And you could provide that with a battery, a chemical cell. There are different ways that you can do this. We'll learn some of the different ways of providing a voltage. But if I have a location of high voltage and a location of low voltage, we know that positive charges will fall downhill from high heights to low heights. So positive charges would naturally want to move to the right in this diagram. However, the positive charges don't move. The positive charges are glued. This is the red is the atomic lattice, kind of a model of the atoms that make up this conductor. They're glued in the nuclei of the atoms. It's rather the electrons or the free charges that are able to move in the wire. So I've got represented them by purple dots here in the graphic. And so the electrons are going to fall uphill. They're going to fall from the low voltage to the high, because remember, high voltage is associated with positive charge and low voltage with negative charge. So the electrons want to move where it's positive. And they can't move in a straight line. We got this kind of zigzaggy path. What the electrons are going to do is, as they get kind of pulled in this direction, they're going to run into the atomic lattice. And so when charge flows through a wire, the electrons take a very zigzaggy path and sometimes even bounce backward, but gradually, and it's actually quite slow, really on the magnitude of only a few centimeters per second that electrons actually travel through wires and buildings and electronic devices. This is called electron drift. Now, not all of the electrons are doing this. In fact, most of the electrons just stay in their nice orbitals around the nuclei. It's electrons that are free to move, that are in the outer bounds or bands, the conduction bands for this metal, that are able to move along the wire. So each atom might contribute an electron or two that are able to be a conduction electron. So electron flow in this graphic is from right to left. However, there's a historical error, so to speak, and I say kind of fortunate perhaps, that when positive and negative charges were first discovered in the 1700s by Benjamin Franklin, or he coined the terms positive and negative, he didn't really know which one of the two was doing the moving in the wires, because you could have a bunch of positive charges flowing one way or a bunch of negative flowing the other way, and it would look exactly the same. So he took a guess, and he had a 50-50 chance as to which was doing the moving, and he guessed wrong. He guessed that the positive charges were flowing and that the negatives were sitting still. So the actual convention in electronics and engineering and science, even today, is to treat electrical current, the flow of charge, as if it were the flow of positive charge. So this is called conventional current. And so the conventional current, the symbol for current is the letter I. The conventional current in this diagram is something that's totally imaginary. It's an imaginary flow of positive charges to the right. In reality, the electrons are moving to the left, but we're imagining that that amount of positive charge is moving to the right. So yeah, I say this is a fortunate error. It sounds like it's just needlessly confusing. However, this current convention to treat charge carriers, the carriers of charge in a conductor, as if they were positive, has a nice side effect. And it has an intuitive side effect in that electrical current, in this sense, will always flow downhill. Because remember, electrons want to fall to higher voltage. They're going to tend to move towards places of high voltage. And mass doesn't do that. If I take this baseball and I let it go, it's always going to fall downward naturally. And so its natural motion is to lose height. It's nice to think about charges that way too. So if you think about electrical current like current of water, a flow of water, a stream of water, water always flows downhill. You can think about electric current or charge, like pretend positive charge, flowing downhill as well. So by metaphor, we could look at this wire and think about it as a hill, with the left end being the top of a hill, the right end, so at a height of positive V, the right end being at 0 V, and then the positive charges, this conventional current flowing downhill and picking up speed as it does so. Mathematically, we measure the current as the amount of charge that flows by in a period of time. So this is on the IB data sheet, delta Q over delta T. So this is just simply the number of coulombs of charge that flow by over a period of time. So the more charge you have flowing by, the larger your current is. And it's the same, we use the word current to talk about water as well. A lot of water metaphors here. If you're looking at a creek or a creek and you watch the water flow by, if there's a lot of current or a strong current, that just means a lot of water flows by per second. And a weak current is just a trickle. Same thing with electric charge. So the unit for current is the coulomb per second, charge per time. This has its own special name, ampere or amp. Is it sometimes ampere, if you want to say, I think it's a French word, ampere is supposed to say, but most people say ampere or amp, amps of current. So, actual everyday currents in a device like, a digital calculator, you might have, maybe 20 milliamps of current flowing through this. So that's 20 thousandths of an amp of a coulomb per second. And wiring, like in this classroom, in the school, or in your home, you might have 10 amps, kind of a common circuit in a house would be a 10 amp circuit. 10 coulombs going by per second. That's a lot more current than you'd find in a device like this. It's kind of the range of numbers you'd find in everyday life. Okay. Now, as current flows through a conductor, we find that this zigzaggy path. So remember, again, we're pretending like it's the flow of positive charge, but in reality, it's electrons moving in this direction. And as those electrons move, they run into the atoms in the lattice. They can't just pick up speed and go faster and faster as they move, but they kind of move at more or less a steady speed as they bounce. And it's kind of like trying to walk through a crowded room and bumping into a bunch of people. And so one of the effects of this is what we call Joule heating, that the electrons are going to transfer energy, mechanical energy, as they run into the atoms in the lattice. They're going to excite them and vibrate them. And so when you run electric current through a conductor, conductors tend to heat up. We tend to turn that potential energy of our charges as they move into internal energy, which is, shows up as an increase in temperature. Think back to topic 3 and the material. So you run a current through a wire, the wire tends to get hot. This is very useful. This is how a lot of electric ovens work. This is how hair dryers work. This is how, a toaster oven works. A toaster, you put your bread in the toaster and electric current runs through little coils of wire and they glow red hot and they toast your bread. Okay. So the collisions that happen in the atomic lattice can be described quantitatively through something called resistance. We say that this conductor has some resistance to flow. If there was no resistance, the charges would just flow in a straight line without being impeded. But they run into the atomic lattice, give off heat, create heat, and they experience resistance. So we can measure this quantitatively. The resistance of a material is defined to be, so this is kind of a funny symbol right here. This isn't the equals sign, it's the 3 slashes. R is, it's the same as equals, R equals V over I. However, it means R is defined to be. So it's not like they just happen to be equivalent. This is the definition of R, just a notation. So R is the voltage per current, a volt per amp. So what is resistance telling me? It's telling me, okay, if I put a certain number of volts across something and then look at how much current I get flowing through it, that indicates my resistance. So if something has a very big resistance, then it's going to have a very small current flowing through it with the same voltage. So big resistance means it's hard to get through. They're inversely related to each other, voltage and resistance and current. The unit for resistance is a volt per ampere. This is called an ohm and is identified with the Greek letter omega, capital Omega. In this relationship, if you were to think about R as being a ratio between voltage and current, you have to be a little bit careful with this, R being a ratio between voltage and current. Sometimes people think of it as a gradient or a slope on a current and voltage graph. So over here, I have an imaginary plot of current versus voltage. And typically what will happen is you increase the voltage across something, you'll see the current go up as well. And then this line right here is going to be the relationship between the two. So if I were to rearrange this expression, I could write this same expression as I equals 1 over RV. If I wanted to write this as a linear function, where my y variable is I and my x variable is v. And it would seem like the slope or the gradient of this line would be the inverse of the resistance. However, this relationship doesn't have to be a linear relationship. For some materials, the relationship is linear, that if you double the voltage, you get double the current. Many materials do behave that way. And if they do, they're called ohmic materials. And we need to differentiate between materials that are ohmic and materials that are non-ohmic. And so the way we do that is through something called Ohm's law. So Ohm's law says the following: current is proportional to the potential difference. In other words, it's a linear relationship if the temperature and therefore the resistance is constant. So one of the effects that we tend to get is because of this Joule heating, as this atomic lattice heats up and starts to wiggle around more and more, is it actually makes it harder for charges to get through. So in a cold wire, these atomic lattice is relatively still. The charges can flow through with minimal collisions, but the more these atomic lattice vibrates, the more collisions charges will experience and the more resistance they get. So for a lot of real devices, as they heat up, if temperature changes, the resistance changes. And if we're thinking about this as being a linear graph, that kind of implies that this is just going to be a constant value. The 1 over R is going to be the slope. But if R changes, then this is going to be nonlinear. So a nonlinear material is called a non-ohmic material. A lot of real life things are like this. Light bulbs are like this. As light bulbs heat up, their filaments get hotter and they become more resistive. Most things do as well. And Ohm's law is a description of a proportionality between current and potential difference. And you can write it, it's just a rearrangement actually of our definition of resistance. We can write I equals V over R. I write this in terms of I. We see that I is proportional to voltage. So more voltage generally gives you more current, but more resistance gives you less current. And probably the most common way of writing Ohm's law is to get it out of its fraction form entirely and just write it as V equals IR. Another famous way of writing it. I think this way is a little more intuitive, where we think about how current is affected by these two things. But this mathematically is the same, P of V equals IR. All right, flip over to the back. Second page of our notes here. Another relationship you should be aware of, if we think about how charge flows through a conductor, is the IB data sheet gives us an equation for the drift velocity. So remember, the electrons, okay, go back to reality here. We're not talking about imaginary positive charge, but the actual motion of electrons is relatively slow through the material. And IB datasheet gives us an equation, and you're actually going to derive this as part of activity 29. It's going to walk you through the steps of where this equation comes from. So I'm not going to go over that here today or right now in this discussion. But in this equation right here, we have a relationship between the current I, the charge density, little n, which is the number of charges per cubic meter. So again, there's lots of charges in atoms. This is just the free charges that are available to move in the material. So usually this would be a given number. Sometimes maybe something we would solve for by knowing the other quantities. But if we know the amount of free charges, and that's kind of based on the chemistry, the atomic structure of the metal per cubic meter, the cross-sectional area of the conductor, so if we kind of slice through it right here, we have a cross-sectional area. Usually it's going to be a circle because the cross-sectional area of a cylinder is a circle. V is the speed, the drift speed, and Q is the charge that's moving. So it's usually your elementary charge, the charge, because it's an electron that's moving, that 1.6 times 10 to the negative 19th coulombs. Okay. And you can just put the magnitude. It doesn't have to be a negative number in this equation. So this is the relationship between current, charge density, area, drift speed, and the size of our charges that are moving. And you'll be using this in activity 29. Generally, we have some different categories of materials, and we talked about these briefly before at the beginning of our topic, and how they interact with charges as they flow through them. Really, we've just been looking at conductors, the way a charge moves through a conducting material. An insulating material, an insulator, has no free or very few free electrons. So basically, the charge density, little n, is going to be 0. If you set little n equal to 0, then I is going to be equal to 0. You're not going to get any current flowing. So insulators do not allow current to easily flow. So rubber, wood, dry air, these kind of things tend to be pretty good insulators. A superconductor is a material that offers absolutely no resistance to the flow of electric charge. There's no energy loss. The electrons don't interact with the atoms at all. They just simply move, and they're in a separate quantum mechanical state. Where they're not interacting at all. It's actually pretty difficult to get them in that state. Usually requires super cold temperatures near 0 Kelvin. Though even in this last year, there's been some recent breakthroughs in higher temperature superconductors. Semiconductors, sort of their own category. Really, semiconductors are very complex. The basic idea in semiconductivity is that you can control very sensitive changes to a material to make it either behave as an insulator or a conductor. And you're doing that by adding tiny impurities to the material, usually bismuth or silicon or common materials that semiconductors are made out of, and affecting, just having very small numbers of charge carriers that you can kind of tweak the charge carriers or their holes, the absence of charge carriers, to allow charge to only flow one direction or the other. Really, I just want you to be familiar basically with that term. You don't need to understand all of the ins and outs of that at this point. The resistance of a conductor. So going back to conductors, a material that will allow charge to flow, the IB data sheet gives us another relationship It's easy to mix these two things up. We've got resistance, big R, and we have resistivity, which uses the Greek letter R, or rho. So this is the Greek letter for R. It's phonetically, it would be RHO, rho. This is a property of the lattice of the material itself. So just depending on what the atomic structure is. So every piece of aluminum has the same value of rho, whether it's a little piece or a big piece. The overall resistance of the material is a composite of 3 different factors. So if we have a piece of wire right here, we've got the length of the wire L, the cross section of the wire A, and then its material, which is its resistivity, rho. The units of resistivity are ohm meters, ohms times meters. So if you want to know the resistance of this wire, it matters what the material is. It matters what the length is. If you have a longer wire, it actually has more resistance because there are more collisions as the charge tries to get through the wire. And it also matters what its cross-sectional area is. If you have a very small cross-sectional area, it's going to create a bottleneck and make it harder for the charges to get through, increase the resistance. Now, for some reason, I'm not sure why, the IB datasheet doesn't give the equation in this form. They write it in terms of rho, but you'll see that it's the same thing. It's just rearranged in terms of the resistivity. But you could use this expression to solve for the resistance. And in some of your problems in Activity 29, you're going to be given the material, a length, and maybe you'll be told the diameter of the wire, and you might have to use pi r squared to find the area since it's a circle, and find resistance or resistivity. Okay, last but not least, you're going to be doing some lab experiments here in Activity 29. If you were in the classroom, we would be doing this hands-on, and we get the sensors out. It's a real shame, but I kind of have to do a simulated version of this just so you get a chance to actually see how circuits work and how current and voltage can actually be measured in a circuit. So there are kind of 2 sensors you need to be aware of, and they're symbols. I'm going to introduce some schematic symbols here in our diagrams. A circle with an A in it is an ammeter, a device that measures amps of current. A circle with a V is a voltmeter, which measures volts. And the way that these sensors are wired in a circuit really matters. And you'll see this even in the simulation, it's going to matter when you hook it up. Ammeters must always be put in series, which means in a row with the wire, because ammeters, a good ammeter has almost no resistance at all. You want the current to flow through the ammeter because the ammeter is measuring the current, but you don't want the ammeter itself to slow the current down. So you need something that has a very low resistance and can just measure the current that's flowing through. The voltmeter, on the other hand, has an almost infinite resistance. You don't want current flowing through your voltmeter. Instead, you want your voltmeter to kind of touch on either side of the object, and you don't want current to leave and flow through your voltmeter. You want your voltmeter to know the potential difference between one spot and the next. So we say that the voltmeter is put in parallel, and the ammeter is placed in series. I'll show you what that looks like here. We got a diagram. And we're introducing some other symbols here at the end of our notes. The way that a voltage source, rather than actually trying to physically draw a battery, which can be many different shapes and sizes, your voltage source schematic symbol is a long line and a short line. The long line represents the high voltage terminal of your battery, which will be associated with the positive terminal of your battery, positively charged end of the battery. And the low voltage, the negative terminal, is the short line. A resistor is an electric device that is intended to do nothing but resist the flow of electrical energy. So it's a conductor, usually a piece of wire that is coated in ceramic and is designed to slow down the flow of electric charge. So the schematic symbol for a resistor looks something like this. And right here I have our first circuit diagram. So there's a bunch of things going on in this circuit diagram. A circuit just means a loop or a circle. Notice that I've got a battery right here. I've got my place of high potential and low potential, and there's a loop, and it comes back to itself. So electrons, what's actually going to happen in this is that the negative terminal of the battery has extra electrons, and since I've provided a conducting path, this purple right here, electrons are going to flow from the negative terminal. They're going to flow through the resistor. They're going to flow through the ammeter, and they're going to go to the positive terminal. However, if the question is which way is the current flowing, remember conventional current is the imaginary flow of positive charge. So the actual direction of I is what's in red here. It's the opposite of what the electrons are doing. Now, in almost every case, that doesn't matter. Whether electrons flow to the left or imaginary positive charges flow to the right, it would do the same thing to the resistor. So, it doesn't matter. It's the conventions, what we're going to go with. So the current's flowing in this direction, always from the high side of the battery to the low side of the battery. So we have an ammeter here. It's designed to measure the current. So notice that the ammeter is part of the path. So it's in series. It's in a row with the battery and the resistor. They're all part of the same loop. And all that current flows through the ammeter. It actually flows through the ammeter, through the resistor, and then it flows through the battery again. There's a chemical reaction happening here in this cell that then lifts it back up to the top high potential. It flows around again, continuously flows. Notice that there's no current flowing through the voltmeter. You don't want that to happen. You don't want the current to come to this spot, take a turn, and go through the voltmeter and never go through the resistor. The voltmeter is just an innocent bystander. It's designed to come from outside of the circuit and measure how many volts of potential difference there are across this resistor. So the voltmeter always comes from outside. The ammeter is part of the circuit. You're going to get a chance to build this. In your case, you're going to build it virtually. Hopefully at some point in the lab, in the classroom, we'll get back in here and we'll be able to build them hands-on. Maybe, maybe not. We'll see. So that's all you need to know for activity 29. Go ahead and get started on that. Again, we'll have all of next class to work on this as well. Free this afternoon to answer questions, and we'll see you tomorrow or then.